So yesterday we ended off when we were talking about the three methods of heat transfer. Okay, but before that, let's go back, kind of review everything that we talked about yesterday. Okay, first thing was the three fates of light when they encounter the Earth's surface. What are the three fates? What are the three things that can happen? Caitlin? Absorption, reflection, and conversion. Okay, things we need to remember. Absorption and reflection and conversion are all affected by one thing. How much of them happens is affected by, or is determined by, single word starts with A. Albedo, right? Okay, so the reflectivity of the Earth's surface determines how much energy will be reflected, how much of it will be absorbed / converted. Okay, the darker the Earth's surface, the more of it will be absorbed. The more the plant cover, the more of it will be converted. Okay, and if it's covered in snow or some other highly reflective surface, most of it will be reflected, and there'll be no energy change in that situation. Okay, so it's important to remember that. Okay, then we were talking about the three parts of the Earth. Okay, so everything is in threes in this lesson. Okay, so we got the three fates of light, then we got the three parts of the Earth: the atmosphere, the hydrosphere, and the lithosphere. Okay, you remember that the atmosphere is the most important part of the Earth when it comes to energy transfers because it's the most fluid. Convection occurs best there. Okay, and then we talked about the hydrosphere and how its job in terms of energy transfers is through the water cycle, okay, through evaporation and condensation, okay, allowing that latent heat to move through the water cycle, and that the lithosphere was mostly just responsible for housing plants, okay, and of course being mostly responsible for albedo. Okay. Then we got to this, the three methods of heat transfer. Okay, we talked about conduction, which is how a metal spoon gets hot, or the handle of a metal spoon gets hot, even though the handle isn't in the hot liquid. Okay, it just conducts up the handle of the spoon by the molecules running into one another. Okay, we talked about convection, and we ended off the day talking about convection and how insulation works. Okay, and I think we at the very end talked about how a quinsy, which is an emergency snow shelter, can keep you warm because snow has a similar structure to fiberglass insulation. It traps air. Okay, anything that can trap air can prevent convection because convection can only move if a convection can only occur, if a fluid, liquid or gas, can move and create a current. Okay, so by having the walls of our houses stuffed with fiberglass, we prevent the air from forming a convection current, and we stop convection from happening. Okay? Similarly, having your wall full of insulation, I don't know if we got to this part or not, okay? But if I've got my wall full of insulation, and it's full of air that's trapped, can conduction occur? Remember, conduction is when can only occur in solid materials, and it would be by the collision of molecules from the inside to the outside. Could conduction still occur? Not very well, okay? Because conduction can't occur through a gas. And what is there a whole bunch of trapped in the fiberglass? Gas. Okay? All those air spaces trapped between the glass fibers. Conduction can't occur through those. Now, are there places in your walls where conduction can occur? Where? Okay, I was thinking heat conduction, not electrical conduction, but yes, you're right. Through your window? Yeah, possibly. I was actually thinking of places like actually in the physical wall. You can't see them, but they're in there. Yeah, the studs. Okay, when you build a house, the house is framed. Okay, so the walls look like this. I can't remember what building code is. There's one every 18 inches or 2 feet, depending on how big they are. Okay, so that means that every 18 inches to 2 feet, there's a piece of wood that is going to be in contact with the outside of the house and the inside of the house. Can conduction occur through that? It can. Luckily, wood's not a very good conductor of heat. Okay, so it doesn't occur much. But if it was minus 40 outside and you ran your hand along the wall, you might be able to find the studs. You'd find a cold spot, and then maybe another one. Okay? The places where there's lots of insulation, you probably wouldn't notice it. Now, if you've got a newer house with 2x6 construction, that's 6-inch studs, okay, you probably wouldn't notice. If you had an older house with only 2x4 studs, you might, okay? You might be able to notice that. Or, if you have a really new house and you have metal studs instead of wood, okay? Metal does conduct heat very well, and you would probably be able to feel the cold spots. Okay, everybody follow me on that? Okay, so this does a pretty good job of preventing conduction and convection. Can any radiation go through your walls? I mean heat radiation, not like gamma rays. Like gamma rays can go through your wall. Okay, but can like heat radiation get through the wall? Are your walls opaque? They are. Then heat radiation can't get through. Okay, things you can do to help that. Make the walls what color? White. Okay, if you have light colored walls on the inside of your house, the heat from inside your house is going to generally be reflected off the light colored walls. If you have black walls, your house will be very dark. And it will definitely absorb radiation because black absorbs all wavelengths of light. Okay, and so you would actually lose some heat by radiation because the walls would absorb it and then be able to try and transfer it through to the other side. Okay? All right, this is why you never see like the inside of a cooler. If you ever open up like a cooler, they're never black inside. They're always white. Okay? It's a reason for that. It's reflective. Okay? It keeps the cold or the heat or whatever you're trying to do in. Okay? All right, does that make sense? Okay, so the three methods of heat transfer are conduction through solids only by collision of particles, convection, which requires a fluid to be able to circulate, okay, and radiation. That's any energy transfer by waves, and that is how energy gets here from the sun. So the way that this would be tested on an exam would be like this. I would give you a question like, you need to design a building that could keep food cold in California. How would you do this? And you would have to explain to me how you could prevent these three methods of heat transfer. Okay, so you put insulation in the walls. What color would you make it? Where would you put it? Okay, stuff like that. Would you put an air conditioning unit on it? Where would you put that air conditioning unit? Okay, all that kind of stuff. How would you apply what you know about these three methods of heat transfer, okay, to a practical situation, right? Or it could do the opposite and say you want to have a solar water heater, okay? So you want to use solar energy to heat water. How would you do that? Okay, well, that means you need to make the water heater what color? Black. Yeah, you want it dark in color. Do you want it to conduct heat well? You do. You want the heat to get into the water through the pipes. Okay? Would you want the water to circulate? Yes, that's convection. You want to, this is how you would harness these things to do a job. Okay, so that's how I'm going to ask. I'm going to give you a practical situation and ask you, how does that work in terms of the three methods of heat transfer? All right, everybody good with that idea? Okay. So, the importance of the atmosphere is this. The atmosphere can transfer energy by local and regional winds, okay, which are a type of convection current. Okay, and air masses can carry energy as both sensible and latent heat. Okay, so the water cycle and the atmosphere kind of work in concert, okay, for that part of it. The atmosphere has to move the latent heat, but it's the hydrosphere that puts the latent heat into that cycle. Okay, what part of the Earth receives the most solar radiation? The equator. Okay, so that's why the equator is generally warmer than anywhere else on Earth. Okay, how does energy get from the equator to here? Exactly, yeah, it's different wind cycles, different wind patterns, okay? It's the movement of the atmosphere that allows that energy to transfer from the equator to more polar or mid-latitude areas, okay? It's all about the second law of thermodynamics. Energy is going to flow from hot to cold. The equator is hot, the poles are cold. It's naturally going to try to go that way. And when it does, it's going to carry air masses that have latent heat. It's going to do all of that stuff. Okay? Later on, we're going to learn about all the wind mechanisms that are present, okay, and making this go on. But know that the atmosphere is most responsible for all of these transfers. Okay, hydrologic transfers, again, that's mostly through the water cycle, okay, and we're talking about putting that latent heat, the energy that's stored by water vapor into the air, okay, the atmosphere can move it to different places, and then when it condenses, it releases that as sensible heat, the precipitation falls to the ground, okay, and energy has been transferred via the water cycle. Okay, so that's the big thing there. Water condensing in the atmosphere releases the latent heat that warms the surrounding atmosphere. Okay, in the sea, currents transfer energy, as does evaporation and condensation of water. So ocean currents are another example of a hydrologic transfer. Okay, they can have a pretty big effect on climate and things like that. So, because we learned that the other day. So definitely ocean currents are going to be a big deal in terms of a hydrologic transfer. Okay, and then lithospheric transfers, there's not much. The lithosphere does not play a very big role in this. Okay, mostly it's just allowing a place for plants to grow where the conversion part of the big three can happen. Okay, so we've got energy transfers and conversions that occur. They're mostly chemical kind of conversions as opposed to thermal. Okay, so big things to remember, because I didn't have a lot of stuff on there the other day when I had this, so maybe just add a couple of little things to the notes you made yesterday. Okay, the three fates of solar energy. One is reflection. If reflection happens, there's no energy change, and that's determined by albedo. Okay, absorption. Energy is gained. Thermal energy is gained. Temperature increases. And it's also affected by albedo. A low albedo means a lot of absorption. A high albedo means a lot of reflection. Okay, and then conversion, photosynthesis. Okay, we convert light energy into chemical energy, glucose, which then fuels the food chains and things like that. Yesterday, I also told you how I would test this. Okay, so just a quick reminder. I would give you a picture, satellite picture of some place on Earth. Okay, and you would have to look at that picture and determine how much reflection, absorption, and conversion would go on. Okay, and explain kind of how much of each would occur and why. All right, so if I was to show you a picture of the mountains in the wintertime, okay, from above, then you would say to me, well, the whole area is covered in snow, so the albedo would be very high, and much of the incoming solar radiation would be reflected. The treetops and some exposed rock might have a lower albedo and absorb some heat energy. There would be very little conversion because the plants are likely dormant because it's winter. Done. You've shown me. I understand what three things can happen to light. I understand what influences how much of each happens and how each one works. That would be a 5 out of 5 kind of an answer. Okay? Conversely, if I showed you a picture, a satellite picture of the tropical rainforest, okay, then you would say to me, well, this area is very densely populated with plant life, so a great deal of conversion due to photosynthesis would occur. There's also a lot of dark colors, so the albedo is very low, and there would be a lot of absorption. Very little reflection is going to occur in this area. Okay, notice that in both of those answers, I mentioned the word albedo and what it meant, okay, and how it influenced reflection and absorption, and I talked about the presence or absence of plant life and photosynthesis. Okay, those would be key points for an answer for that type of question. Okay, questions on this stuff? All right. So I'm going to give you about a 3-minute break here, and then that many, 3-minute break. Okay, and then we're going to move on to global wind patterns. Okay, we've got some stuff to talk about there in terms of all these atmospheric transfers that we just talked about. So I'll give you a quick kind of 3-minute break, and then we'll talk about that stuff. Okay, so we're going to look here now at the patterns that wind shows us, okay, on Earth. Right, so we got to look at how energy is distributed. Obviously, most of it lands around the equator, okay, and then has to be transferred from the equator by the second law. Okay, that would be convection, conduction, all that kind of stuff. Okay, understand the role winds play in distributing that energy. Okay, know what the Coriolis effect is, okay, and how it distributes energy, and recognize that global wind patterns are a product of both convection as well as the Earth's rotation. Okay? Something that people don't often get or understand is that the atmosphere and the Earth are not physically attached to each other. Okay? So when winds are moving or the air is moving, the Earth can actually move under them. Okay? The Earth can rotate, and the atmosphere doesn't necessarily have to do the same thing the Earth is doing. Right? It ends up being kind of like if you're in a moving car and you stick your hand out the window. It's not windy, but it feels like it because you're moving through the air at a high rate of speed. Well, the same thing can be true for the Earth's rotation. The Earth can actually rotate under its own atmosphere, okay, or have the atmosphere be moving in the opposite direction of the Earth's rotation, okay, which can make it feel like it's windy, but it isn't. Okay? And it can also make it seem like winds are coming from a different direction than they actually are, because the Earth is moving under its own atmosphere. Okay, so that's kind of what we're saying here in the third point. Okay, so the Earth's atmosphere is always moving. Okay, and there are certain patterns to that movement, but it doesn't really follow the Earth's rotation. Okay, and that's because the Earth is always trying to eradicate imbalance. Okay? All things are always trying to seek equilibrium. Okay? That's what the second law of thermodynamics is all about. It's about achieving thermal equilibrium, transferring energy from hot to cold. Right? So what's always going on, okay, is that the Earth is rotating, and the Earth rotates this way. Okay? So you can see in the diagram, okay, this arrow here denotes the direction the Earth rotates. That's why, if we were over here in the dark, the sun would appear to rise in the... Oh God, you guys don't know what direction, where the sun rises? In the east, right. You had me right there. Okay, so when we rotate into the sun, okay, it looks like the sun comes up in the east, actually just us rotating underneath it. Okay, and then it passes overhead, and as we get over here, we're looking to the west to see the sun as it sets behind us. Okay, so this is the direction the Earth rotates. Okay, if air is trying to move from, let's say, the equator to the poles, or from the poles towards the equator, it gets deflected. It's trying to move straight, but the Earth is rotating underneath it. Makes it seem like it's going a different direction. Okay, that's the Coriolis effect. We'll talk about that in a minute. Okay, everybody all right with that? That's the way the Earth rotates. Okay, almost all the planets rotate that way, except Venus, oddly enough. Venus rotates incredibly slowly in the other direction. Only planet in the solar system that does that. Very, very strange. Okay? And another weird thing about it, its days are longer than its years. It actually goes around the sun faster than it rotates on its own axis. This way, the wrong way. Okay, so nature doesn't like imbalance.
Why does it rotate the other way?
No one's really sure. Could have been like a large impact that possibly affected its rotation. Also, not being closer to the sun and not having the moon can also affect rotation. Like Mercury is tidally locked to the sun, which means the same side of Mercury always faces the sun, and its year is the same length as its day. Same as the moon. The moon is tidally locked to the Earth. That's why we only ever see one side of it. Right? If you hadn't noticed that. We only ever see one side of it, but the moon always looks the same. The other side of the moon looks totally different, but we never see it. Okay? Because its rotational period is the same as its orbital period. So the same side always faces west. Okay, so it may be that Venus is just in the process of being tidally locked and it's slowing right down. Okay? As the moon gets further away, the Earth's rotation slows. Okay? Every year, our period of rotation, our day length, increases by like 6 milliseconds. Yeah. Okay? Because as the moon gets further away, our period of rotation gets slower and slower. Okay? If you trace it back to when the moon was formed by that massive collision with Earth, the Earth was spinning at 6 hours. So, and the moon was 12 hours, and the moon was going around every 6 hours, or something ridiculous like that. So it was very, very different. And you can imagine watching the moon go across the sky like that, except that the moon would have been huge because it would have been so much closer. Okay? Now imagine what the tides would have been like. Okay? I mean, look at the tides now, right? You go to the Bay of Fundy and the ocean goes out like a full-on kilometer and a half. Okay? Well, imagine the moon's way closer. It's going around the Earth like this. It would be like somebody taking a bathtub and sloshing it back and forth. Okay? Like the ocean would like slosh inland about 50 kilometers and go back the other way. And it would have been a crazy time to be alive. But we weren't, because that was like billions of years ago. Yeah. Except the atmosphere was also a lot different then. It would have been poisonous and we would have died. There's that.
How does the atmosphere change?
Well, when Earth first formed, the gases were just different. Like the way the Earth formed with all the collisions and stuff would have had a different blanket of gases. And then as, the Earth cooled, a lot of those gases condensed or, things like that, and the oceans formed. When life started to form, it took out the carbon dioxide and put oxygen into the atmosphere, all kinds of, like the Earth's atmosphere has changed a lot when it was primordial. Okay, so nature doesn't like imbalance. We know that. We just talked about that. It's always trying to seek a thermal equilibrium, which we'll basically never achieve, okay, but it's always trying to. And so these variations in temperature and energy create variations in pressure, okay, and that results in air movement from one place to another. Right? If you ever watch the weather on the news or anything like that, okay, the weatherman's always talking about, the meteorologist is always talking about, they got this high pressure area over here, this low pressure area over here, and the wind's going to do this, and it's going to curve around these things, and it does all this stuff. Okay, that's because it's always trying to achieve a balance. Okay, and that's going to make the air move. All right, so wind in turn transports heat energy and moisture, and that influences global climate. Okay, so the jet stream is a special wind mechanism that helps to transfer energy from more equatorial areas to more northerly areas, in addition to convection. Okay? So the jet stream is a high altitude, very high speed wind, and its location changes day to day. Right? So the jet stream is about 1 to 3 miles thick. It's right at the very top of the troposphere, so it's not like we notice it at ground level. It could be a problem if you were on top of a very tall mountain, like Mount Everest or K2 or something like that. If the jet stream were to pass over the mountain, you would suddenly be in gale force, beyond gale force winds, because the jet stream goes very, very fast. Okay? And like I said, the jet stream's location changes because it can be pushed around by centers of high and low pressure. Okay? So in this extreme kind of case, the jet stream actually went around like this, which it rarely does. It rarely goes backwards, okay, like this. It mostly just goes from west to east. Okay? Which means if you're on a plane and you're going from west to east, you can catch the jet stream and get pushed along by it, which means you might arrive early or the plane might use less fuel. If you're flying east to west, you have to avoid it. That's an ocean current, but it's like that. Yeah, that was the Australian current or something like that. But it's like a jet stream. It's like that. Yeah, it's just in the ocean. So this jet stream can move around, and when it does, it moves air masses with it. So if I've got this jet stream here, and it's moving around this high pressure area, okay, what it's going to do is it's going to pull cold air down. because as it moves through, it's going to cause some movement of this air, okay, and it's going to push the cold air down. This would be what would happen if this happened in the summer. We would get into a very rainy, like thunderstorm kind of cycle, right? And actually, you can see that where the jet stream comes down is right down Alberta here, like right down Highway 2, and then look where it goes through here. What's this area called? Has a nickname. No, not Murica. What's the other nickname? Tornado Alley. This is Tornado Alley. This is like Kansas and Oklahoma and Ohio and places like that. Okay, that's Tornado Alley. So when you get the jet stream moving through there and pulling cold air, coming into contact with tropical air, okay, you've got the two things that can make a big storm. Moisture, cold. Boom, put them together, you get big rain, you get unsettled conditions, okay, stuff like that. If this happened in the winter time, this would be a polar vortex. You know, when we get thrown into the deep freeze and it's -40 for a month. Okay, that's the same idea. If the jet stream gets twisted, okay, it'll just start pulling all this cold Arctic air down, okay, and it creates a vortex, polar vortex, okay? All right, so the location of the jet stream is going to influence what kind of air moves in. So here, it's pulling cold air, but when it goes out to sea over here, when it comes back in, it's going to bring in a bunch of moisture from the ocean, and it's going to cause changes in weather. So if we're about to get a change in weather, you can bet that the jet stream is about to move. Okay, either north and south or east and west, something about its position is going to change. And that's one of the things that meteorologists are always watching. Okay, they're watching the position of the jet stream because they know if it changes, it's going to start bringing air in from other places, and that can cause changes in the weather. If its position is stable, our weather is pretty stable.
How can we measure it when it's just wind?
Satellite. They can see the effects of the jet stream with satellite, like with radar, satellite radar and stuff like that. They can see the position of it. Plus, they can watch the movement of clouds. Okay? They can see where the jet stream is being moved around.
Or like the Chinooks determine with the jet stream?
The jet stream can certainly affect them to some degree, but we don't get a lot of Chinooks in the summer. Right? They're mostly a winter thing. And so yes, the jet stream would influence that to an extent, but I mean, Chinooks kind of make themselves too. Okay, if we get air coming over the Rockies from BC, that's usually what causes it to happen, and that's generally the direction that wind goes. In this particular situation, our prevailing wind would not be happening. Our wind direction in this situation would be from the northeast. Okay, weather-wise, you got a northeast wind here, nothing good is going to come of that. Okay, it's either going to just get brutally cold, or it's going to get stormy, or both. Okay, but yeah, northeast wind for us is a sign that there's a weather change coming, because that's not typically the direction the wind comes from.
Do we know how it was created?
Do we know what, sir?
Do we know how it was created?
The jet stream?
Yeah.
How I couldn't tell you how it was created. It's there. It's always around. I couldn't tell you what necessarily causes it, other than differences in temperature and pressure. And its intensity increases and decreases. Okay? So it's always there, but sometimes it's not very intense, so its effects are basically non-existent. Okay? And then other times it gets incredibly intense and does stuff. Okay? Now, this is only a northern hemisphere thing. There's no jet stream in the southern hemisphere, so there could be some continental landmass influences for that as well. Does that make sense? All right, so jet stream is a pretty big deal, okay, in terms of moving large air masses around, and especially causing changes in weather. Okay, so that's the role it plays. So if I was to ask you on a test, explain how weather changes may occur, or how energy could be transferred from equatorial regions to polar regions, would you mention the jet stream?
Yes.
Yes. Okay, you'd also mention convection and things like that. Okay, but jet stream would certainly need to be part of that answer. It does play a big role in that. Okay, global wind patterns. So prevailing winds, absence of the jet stream, because the jet stream can cause changes. Okay, prevailing winds, okay, is what we're going to talk about here. Which direction do our winds prevailingly come from? west, southwest, okay? And it's pretty evident around here almost all the time that's what it's doing, although lately, because we have a change in kind of season coming, that we get kind of differences, but most of the time out of the southwest. If you go further south from here, okay, if you go down to like Lethbridge, Pincher Creek, you can tell the wind almost always blows out of the southwest. You just have to look at the trees. They're all bent that way, okay? It's that thigmotropism thing we talked about in biology, okay? The trees all grow leaning to the east because they're always getting blown from that direction, okay? It's also why there's a massive wind farm down there. The windmills are always turning and they almost always face the same way. Although the other day when I came home, they were facing the other way. They were facing north. The wind's coming that way. Okay, most of the time they face the southwest. Okay, because that's generally the direction our winds come from. And here's why. So at the equator, okay, hot air rises. The equator obviously gets the most solar energy. So at the equator, we're going to have hot air rising, and that's what we see here. This and this, okay, are convection currents. Okay, this is called a Hadley cell. Each one of these is called a Hadley cell. I'm never going to ask you that. Okay, but we've got hot air, okay, rising at the equator. And when hot air rises, air from further north has to move in to replace it. Because if the air just went up and nothing moved in to replace it, you create a vacuum. Right? That's not going to happen. So the hot air is going to rise right here. It's going to go up. And then warm air is going to come, well, because it's near the equator, it's warmer. Okay, it's going to move in to replace it. Now this air that's risen can't fall back down because air has already moved in to replace it. So you start getting a convection current. You start getting a circulation of the air. Okay? So if you're near the surface, or standing on the Earth's surface, near the equator, you're generally, the wind is always trying to go from north to south. But the Earth rotates this direction underneath it. And so even though it's trying to go from north to south, it feels like it's coming from the northeast. Because the Earth rotates under it while it's doing it. Okay? And that creates what we call the trade winds. Near the equator, winds almost always come out of the east to northeast. Okay? They're called the trade winds because that was the way that people that were trading things could get from the old world to the new world. Okay? They would sail south along the coast of Europe, down kind of Spain, Portugal, that kind of area, and they would catch the trade winds, which would take them over to the Americas. Okay? Kind of in this area, kind of South Central America, and then they would ride the currents up the coast of the United States and Canada. Okay? Do all their trading, and then they're into a different area where the prevailing winds are out of the west, and they would use them to sail back to Europe. So they would run this big cycle, okay, that would allow them to, because all they had was sailing ships, right? They didn't have motors, right? They would just use the winds, and that's how they would get to the Americas and then back home. Okay, so near the equator we get the trade winds. Okay, so it's important to know that near the equator we get trade winds, and those are easterly. Okay? Winds are always named from the direction they come from. Okay? We get westerly winds because they come out of the west. Okay? At the equator, they get the trade winds, which are easterlies because they come from the east. Now, as we get out of this area here, and we get to what's called the horse latitudes, which is about 30 degrees north of the equator, there's a shift. And what happens here is that air that couldn't fall back down, that had to circulate, is now starting to fall back down because it's entering the area this air vacated, and it actually gets pushed along the surface as it goes north. Okay? Now, in this latitude, this air that's, even though it's been aloft, is still warm. Okay? And so this warm air moves along the surface trying to go north. As the Earth rotates underneath it, it deflects it the other way. Okay? So winds that are moving from south to north get deflected this way. Winds that are moving from north to south get deflected this way. So in between these two latitudes, we get prevailingly westerly winds. Okay? So all through the entire United States, they would have prevailingly west winds. Okay? And for most of kind of, let's say, the southern parts of Canada, same deal. Okay? We would be in the westerlies. Now, here where we live, we're kind of at the transition between the westerlies and what we call the polar easterlies. Okay, and that's why in Alberta, if you don't like the weather, wait 5 minutes. Okay, because that's how things go here. That's how we roll in Alberta. Okay? Because we're right at this transition, sometimes we're affected by the polar easterlies, but most of the time we're affected by these westerly winds here. Now, once we get to this area here, so this is the area that we live in, but once you get past this, there's another transition into the polar part. Okay, and at the polar part, instead of having air moving along the surface in a northerly direction, air is actually rotating like this. That's our polar vortex. Okay, the air is always spinning like this. Okay, but because the air is trying to move from north to south again, it gets deflected this way, and you get typically easterly winds. All right, so that's how we get prevailing winds. Prevailing winds are a combination of convections trying to happen, but the Earth is rotating underneath it while it happens. Okay, so winds get deflected by the rotation of the Earth. Okay. Everybody all right with that idea? Okay. So what this actually creates is 3 different bands of weather. If you actually watch the Earth, you can actually see that clouds near the equator always move from east to west. Clouds above that always go the other way. It almost looks like the Earth is doing this and has different parts that are rotating different directions. Okay? Because the clouds follow the direction of those currents. Okay? And then at the pole, it's doing this. Okay? So that's what we see there. Okay? We've got those again. Those cells, those convection currents. Okay? We've got air that's going along the surface. When it gets to here, that air is comparatively warm, so it goes up, okay, gets to here, and it's driven down, okay, and we get those circulation patterns. Okay? Earth is only big enough to have 3 convection patterns per hemisphere. Okay? So 6 in total. Bigger places can have more. Okay? And this is incredibly evident at Jupiter. Okay? Jupiter has many bands of this, and because of the nature of its atmosphere, you can see it as almost striping on Saturn's in Saturn's atmosphere. Okay? And I'll show you a video here, but you can actually see some of the video that they've taken. It literally looks like part of Jupiter goes this way, part of Jupiter goes this way, another part goes this way. You can actually see the parts going past each other in opposite directions. Where those bands interact, storms will happen, like this one. Okay? Jupiter's Great Red Spot is right on the border between winds trying to go this way and winds trying to go this way. And that's what feeds that storm. That's why it's raged for hundreds of years. It's actually fading now. I'm actually kind of observing it. It's getting slowly smaller. Right? So it might actually go away at some point. Right? But for hundreds of years, that storm has been there. And it's because winds on one side are going one way, winds on the other side are going the other way, and it just feeds the rotation. It's a super giant hurricane that's bigger than Earth. All right, I'll show you what this looks like. Does the same thing happen in the southern hemisphere? It does, okay, but it's opposite. Okay? So the winds are still going to be deflected. They're still going to do the same thing, but from the southern hemisphere, the perspective is opposite. Okay? All right. All right. I'd like you guys to try these questions here. Okay. So just write some answers for these good complete sentence answers. I'll give you a few minutes, and then we'll go over those, and then we're going to look at the next thing. So, first thing we want to do is describe the effect of unequal distribution of thermal energy, okay, on both Earth and on the temperature of the atmosphere. So, at the equator, they get way more solar radiation than we do at the poles. Okay? That means it's going to be hotter there. The second law of thermodynamics wants to gain a thermal equilibrium, so energy must move from the equators towards the poles. It does that by convection, which which means the hot air at the equator rises, cooler air from the north moves in to replace it. The air that's moved aloft is going to then circulate in a northerly direction, carrying with it both sensible heat and latent heat, the moisture, okay, moving in a northerly direction, right? And that's going to attempt, or at least somewhat rectify, that energy difference. Obviously, it's never going to completely do it because the equator is continually getting more and more solar energy than the poles, so it's always naturally going to be colder that way, but energy is naturally also going to flow that direction. Okay, second question. Explain how the Coriolis effect influences the direction of winds in the northern hemisphere. Okay, because of convection, air is constantly moving. Near the equator, air tries to move from north to south. The Earth rotates under it as it does so, causing it to feel like it's been deflected from straight north to an easterly direction because we are moving into it as it moves from north to south, making it seem like it's coming from the northeast. Okay, so everyone kind of follow me on that? It's trying to do this, but we're moving into it while it does, so it feels like it's coming from the northeast. It's just like I said, if you were, let's say like even just riding your bike. Okay, if you're riding your bike and you're, riding down 32nd Street, so you're going straight south, and there's a really strong wind straight out of the west, to you it's going to feel like it's actually a little bit deflected because you're moving into it, okay, while it's trying to do this. Okay? The end result would be if you aimed your bike straight and it was super windy, that you would go in this direction. Okay? You'd go somewhat southeast as a result of it. Okay? That sort of makes sense? It's what we call vector addition. These two vectors go together in this way. All right. What are the trade winds and where do they occur? Okay, so trade winds are from what direction? East. Yeah, they are easterly winds that are located where? Okay, some of them are in the ocean, but some of them are over land. I was thinking of a particular latitude. They are near the equator. Yeah, they're within 30 degrees latitude north or south of the equator. Okay, and what are jet streams? Okay, strong streams of winds that can change weather patterns. Their location is influenced by centers of high and low pressure. And those winds are where? Close to the surface or at altitude? Yeah, high altitude, at a high altitude. They're not near the Earth's surface. Okay? They can influence what goes on at the Earth's surface, but they themselves are at a high altitude and are 1 to 3 miles thick. Okay, so they're a big deal. If you've ever been on a plane and encountered a lot of turbulence, you were likely crossing the jet stream. And what a pilot will do is then try to descend so that he gets out of the jet stream. Okay, so if you had a particularly rough flight, that could be part of the reason. Okay, if you had a nice, smooth flight, but then at one point it just got really, really shaky, okay, the pilot will usually try to change altitude to get out of that. All right, questions on any of those?